So the development was very old, is actually very old. It came in 1856, you can see, and it, the Markov was from Russia. He's a Russian mathematician who helped to develop the theory of stochastic process, especially called as Markov chains. Okay. Based on the study of probability of mutually dependent events, his work has been developed and widely applied in the biological and social sciences. Now let us see an example what exactly is Markov chain or Markov model. Now we are going to see the first order Markov say model where the next event depends on current event or status only. Okay, so next you can say status also. Next status of the system is dependent on only current status. Okay, not anything else. So if that is the case, so if today is sunny, whether there will be rain tomorrow. So you have to predict the next state based on current state. So you can predict from sunny to rainy or rainy to cold, then cold to sunny, rainy to sunny, okay, then cold to rainy, and from cold to sunny or sunny to sunny, then rainy to rainy, and then cold to cold. So these are the states of our example. So our example is like this, that we have to predict what will be tomorrow's day, how it will be. So we have three states of our system. First state is sunny, then rainy, and then cold. So these are our states of the system or model. Then we have a transition from sunny to say rainy. Say day 1 is suppose sunny, then what will be day 2? You have to do a prediction. So there is a chance, 80% chance, that when it is sunny, next day is also sun. Okay, so this is the probability of occurrence of the state. Suppose I call sunny as S1, rainy as S2, and cold as S3. So transition from S1 to S1 to S1. Okay, so it was sunny, then again you will see a sunny day. So there is a chance of 80%. Then rainy to rainy. So suppose today is raining, then tomorrow it will rain, is 60%. Then cold to cold is 70%. Then see this transition. Say sunny to rainy, there is a 0.19 or 19% chance. And then from rainy to sunny, there is 0.1% chance. 0.1%, it's 10%. It's 19% and 10%. Then we have different probabilities for different events, say 20% chance from cold to sunny, then 1% chance from sunny to cold. So there won't be direct transition as such, but if at all there are some events like this, so it will be just 1%. Then we have rainy to cold is 30%, and then cold to again rainy is 10%. So like this, we have the Markov model with different states. So we have to first of all decide the states of our Markov model. What are the states? So states can be S1, S2 up to Sn. So there are n different states of a Markov model. Then we have to have a transition probabilities from one state to another state. How I will go, how I can go, what is the chance from say S1 to S2 or S2 to some S3 and so on. So all this information we have to gather and make a probability table called as state transition probability table or matrix. So here we will represent Aij as the entry in your matrix of state transition probabilities. This will Aij is the probability of state next state. Qt plus 1 stands for next state equal to Sj. So next state is Sj when you are in current state Si. So given the condition that you are in Si state, suppose Si stands for rainy, say this is rainy, what is chance that you will face sunny day next time? So it is the probability of sunny given that today it is rainy. Okay, so this is the entry as Aij. So when I say Aij, I am transiting from Si to Sj, state Si to state Sj. Now you have some initial distribution of probabilities, so that is represented by pi I is equal to some probability of being the beginning of your activities. What is the initial probability, what state you are in at the beginning of this model, so that is given by pi I. Now when I want to define a Markov model, I need to define states. Say for our problem of this sunny, rainy and cold, say state S sunny is sunny state, then S rainy, S cold. These are three states of my problem. Then I have a probability matrix called as A matrix. This is a standard practice to write A for transition probabilities. So transition probabilities here I am writing as 0.8, which you can see is the probability of sunny to sunny. So here I should write sunny, then rainy, then cold. Similarly, this will be sunny, rainy and cold. So 0.8 here indicates sunny to sunny transition. So this is the current state and this is the next state. So when I say 0.19, so 0.19 is the probability from this sunny to rainy. Okay. So currently I am facing a sunny day. What will be tomorrow's day? Tomorrow's day, what is chance that it will be raining? So it is 0.19. Then this 0.1 is from rainy to sunny. So where it is? It's from rainy to sunny. Okay. So you can fill all these entries, different probabilities you have, and then you can make a matrix. Now what is important thing to note is that sum of this row is 1. What it means? So when you are transiting from sunny to sunny, sunny to rainy, sunny to cold. So suppose I take this sunny, self transition is 0.8, then sunny to rainy is 0.19, and then sunny to cold is 0.01. So sum should come to 1. So that is the main thing. You will see that this row number 2, which stands for rainy. So you can check here, this is 0.6 plus 0.3 plus 0.3, that is 0.9, and then this is 0.1. So from rainy to other state transition, if you sum the probability, it should come to 1. And this is also 1. So this you should remember that horizontally you should have a row sum is equal to 1. If that is not the case, then something is wrong in that data. Okay, you have to have a row sum equal to 1. Now initial state distribution is like this. That means this is state sunny, then this is rainy, and this is cold. So this is state like this. So this is the initial distribution given to you. So this is the beginning of your model. At that time you assume that this is the chance, and here onwards you will try to predict. Okay, so you should start with some probability and say you are being provided with initial guess, and then you will start predicting next. Now if you are given this model means you will be supplied with matrix A and the initial state of distribution, so pi. So these two things are given, then you are provided a Markov model or a Markov chain. Now suppose I have a question, what is the probability of sunny, rainy, cold? That means day one is sunny, day 2 is again sunny, day 3 is rainy, day 4 is cold. If this is the question, then how you can find out the answer? Now we will use the property of Markov chain, that our current event or status will affect the next one. So or the future event will depend on only current event. So when I start my problem, I have the question sunny, rainy, cold. So I will start with the probability of sunny itself. So probability of sunny, there is no previous event because this is the first event. So I will write probability of sunny, and this information I will obtain from this pi I. So pi I is giving me the distribution of the initial state. So there it is, sunny is 0.7. Then multiplied by the second conditional probability that given current state is sunny, then what is chance that next day is also sunny? So go to your table, transition table, you will see that this is sunny and this is sunny. So this 0.8 is the probability of this event. So we are finding out say this 0.7 multiplied by 0.8. Now next, multiplied by the next step is from sunny to rainy. So I am taking now this pair. Current state is sunny and the next state is rainy. So this I should write rainy given sunny. Okay, so go to the table where it is rainy. Say this is rainy, then you want sunny. Sorry, from sunny to rainy, right? From sunny to rainy. So this is rainy. So this is 0.19. So this will be 0.19 multiplied by next state is from rainy to cold. So from rainy to cold is next state. So go to the table and see where is rainy. So this is rainy and next state is cold. So this is, I think, right? Okay. So this is sunny, rain, right? So I think this is some mistake here. So if you multiply this number 0.7 into 0.8 into 0.19 into 0.3, then whatever probability you get, it will be a small number, something like this, and this will be the probability that you will face sunny, then rainy and cold sequence. So a probability that you will observe such a sequence is given by this product. Okay, it's very simple. I hope you can understand this thing. It's very straightforward. Only thing you will remember is next state depends on current state. Then it is Markov first order. Suppose I say second order, that means current state, or sorry, next state depends on current state and previous state. So things will be more complicated, but this is a simpler Markov chain where next state depends only on current state. Then question is, what is hidden Markov? Because the title of your chapter is hidden Markov model. We have seen only Markov model. So Markov model is basically the model which states about transition from one state to another state. Okay, suppose there are three different states, so you can have this relation. There will be a self transition as well. So you will define this transition from one state to other state with the help of a matrix called as A. So you will write here S1, S2, S3, which is the current state, and this side you will again write S1, S2, S3. This will be next state. Then all the corresponding probabilities, say 9 entries, will be provided. Along with this, you will be provided with initial guess or initial state system. So initial state will consist of again three numbers. These are the initial probabilities of the three states. You may have number of states, so you may have states like S1, S2 up to Sn. Now if this is the case, then it is simple Markov model. Now, what is hidden Markov model? Assume that you are currently in a lockdown position and you cannot see outside world. So what is the current weather outside? You are not able to observe. So all these states, that is sunny day, rainy day, cold day, they are hidden states. You cannot directly suppose monitor these states outside. Say you're locked in some room, there is no window to that. You just are somehow there and you cannot see outside. So what exactly happening outside, whether it's sunny, rainy or cold. But what you can observe is that a person who is serving you, suppose food in that room, is wearing a sweater, he's wearing some umbrella or coming with some umbrella or coming with wearing with a short. You can observe these things. You cannot see the states that is sunny, rainy or cold. This you cannot see. But what you can observe or what you can see, those things are called as observable states. The observable states, what you can see is whether a person is coming with sweater, he is having umbrella or he is coming with a short. These suppose three things you can observe. Okay. Now based on this, only this information, you have to estimate what's going on outside. Okay, so what are the status of different hidden states by monitoring only observable states? If this is the problem, then this is called as hidden Markov. Markov is when you see directly states, you can see all the states, what are the current states, what is the current state, what is the next state. So is this, if this is observable to you, then it is simple Markov. But when you have states of your system not observable directly, but you can have a guess of that status with the help of some other observable states or information. You have some other information, from that you have to guess what is the status. Say for example, if you observe the behavior of your friend, then you can predict the mental status of your friend, whether his mood is happy, whether the mood is bad. Okay, like that you can guess from the other observable variables. So that is the hidden Markov model. Now here there will be one extra table given to you along with the earlier table A. The earlier table A is state transition matrix, same as the previous one. So you have sunny day, then sunny day as next day, then rainy day as next day, cold day as next day, then rainy and again cold. So this is same as the previous. Now given a sunny day, suppose the status of the system is sunny, then wearing sweater, the chance is 0.1. Coming with umbrella is 0.4 and wearing shorts is 0.5. Okay, so this is the these are the probabilities when the day is sunny. So again, sum of this row must be 1. Now given day is suppose raining, then wearing sweater is 0.15, coming with umbrella is 0.8, wearing shorts is 0.05. Okay, so like that I have a table B which is called as emission matrix. Now see, I have status suppose S1, I have status or state S2 and then state S3. So there is a probability suppose given to me to transit from one state to other state. So this is a matrix A. Now when you are suppose at state 2, you can emit different symbols or you can have different uh, indications. So as I have an indication here, sweater, umbrella and short, and they have their corresponding probabilities. So when I have say S2 stands for suppose rainy day, then the probabilities for different indicators are 0.15, then 0.8 and then 0.05. So these are three probabilities when my state is S2. Again, when my state is S3, I have three different probabilities. When my state is S1, I have again three different probabilities for same indicators. So indicators are three. So depending on your problem, you can choose many such features and then you can solve your problem. So suppose for the simplicity, I am just taking three indicators that are observable. So the states which are observable, they are here: sweater, umbrella and shorts. The states which are not observable within from that room which is completely closed is sunny, rainy and cold. So sitting inside the room, you want to predict what is outside. You don't have access directly to the outside world, but what you can observe is the person who is serving food for you. So you can see that person and see the clothing of that person or what that person is carrying. So that information you can access directly and then you can predict. So this is some hypothetical problem. Now the initial state is the chance that you have sunny, rainy or cold. So they are equally likely, so I'm just writing 0.33, 0.33 and 0.33. Now the question is, what is the joint probability that you have an event or a sequence of events that you see day 1 as sunny, say day 1 as sunny, day 2 as sunny, day 3 as rainy, day 4 as cold, and the person who is coming to you is having umbrella for day 1, then shorts for day 2, then umbrella again for day 3 and sweater for day 4. So this is a combination of hidden states and observable states. Now suppose I have everything with me. I know table A, I know B, I know pi, then what is the joint probability that this thing will happen? Say day 1 is sunny, day 2 is sunny, day 3 is rainy, day 4 is cold, and the person carries umbrella for day 1, shorts for day 2, for day 3 again umbrella, then day 4 is sweater. That means I am interested in joint probability of hidden states and observable states. So these states are not visible. What I can monitor is only this information, D1, D2, D3, D4. Now when I say I have everything, so this information is with me somehow, then I can calculate the joint probability for this particular sequence of hidden states and observable states. Now the first part we can easily do. We have a transition beginning at sunny day, so there is no previous day for this, so it's sunny. So this you can obtain from the pi I given to you into sunny to sunny, then rainy to sunny, then cold to probability of rainy to cold. Okay. So this is directly coming from the table multiplied by the probability for observing different things. So what you are observing? So you are observing for sunny day, what is chance of having umbrella? So this is a pair for day 1. Then day 2 is sunny to sunny. And what is chance that you will see a person with short? Then day 3 is sunny to rainy. So what is chance that he will come with umbrella? So this is day 2, this is day 3, and day 4 is sunny to cold, rainy to cold. And when you have cold, what is the chance that a person will come with sweater? So these 8 probabilities you can directly obtain from this information. So I can see there it is 0.33. Then the next is sunny to sunny is 0.8. Then rainy to sunny, sunny to rainy, so this is 0.19, and so on. So if I substitute everything from these two tables, that is state transition matrix and emission matrix. Why it is called as emission? Because these are the symbols which are observable. So the sweater, umbrella, shirts, these are observable symbols that are coming from the different states. Now when you multiply, straight away you will get the probability as 0.002166912. So this is the joint probability that you will observe a sequence of 4 days, say day 1, then day 2, day 3, day 4. For day 1 you have observed that there is umbrella. For day 2 you have observed short. For day 3 you have seen again umbrella, and day 4 you have seen a sweater. So this was your observation, and the true states were sunny, sunny, rainy and cold. Now actually there are 3 problems that we see in HMM. The first problem is called as evaluation problem, where we will deal with a problem like what is the probability that the observations O given a model theta has produced a sequence of T observations? Okay, what is the probability that a given model has produced certain sequence of observations? Now, for example, what this means is, say you are doing some speech recognition or you say person recognition, and you have some HMM model for, let us say, 10 persons. Then you are inputting some sequence of sentences to these models. So the model number 1 is trained for person 1, then person 2, person 3, 4 and 5. Okay. Now there is a typical style of speaking of everybody. So same sentence if I utter and you utter, then obviously there will be certain change. And the HMMs will try to capture those typical styles of individuals. Now when I feed from this side some sentence of some X person, then this sentence will go to every HMM, or this sequence will go to every HMM, and then the job of this model is to verify whether this person number 1 has spoken this or not, or 2 has spoken this or not. Like that, it will try to give probability of producing the observations given this model theta 1. So this theta 1 is nothing but a model A1, that is the matrix A1, matrix B1 and pi. So these three things for person number 1 are stored separately. Then there is a model theta 2, there is a model theta 3 and so on.